Okay, so I wanted to talk about an old project of mine. This is from a decade ago almost, 2012, to write a turtle graphics for this little FIGnition board. It was a pretty fun little project, and I learned a bit while doing it. This is the FIGnition itself. So it's a project by Julian Skidmore. I think he's in the group. Maybe he'll give a talk on it at some point. But briefly, it's this little board. It runs FIG4th. It's an Atmega 168, little 20 megahertz crystal, 8K of SRAM, and 384K of flash. It generates audio, can generate audio, and generates a composite video signal. So you can just plug this into a TV or a composite to HDMI adapter, and you're good to go. It has this 8-button keypad for input. A little bit of a strange input system, but it's kind of fun. This is how I actually implemented the first instance of this turtle graphics, is just on this keypad. So single presses of buttons give you arrows and space, and I think backspace, and then holding down multiple at a time, you can get the whole alphanumeric set, which is pretty cool. So of course you get a FIG4th prompt, and you can just type there directly. It also has a flash block editor that lets you edit 500 character, 25 by 20 character blocks in Flash and store them there permanently. I should also mention though that the keypad, for one, there's a separate module which I've never used, but it adds a PS2 interface for this, a keyboard interface. You can use a regular keyboard. And you also can transfer text files from a host PC to the device using AVR Dude. It transfers to EEPROM, and then there's some commands to transfer the EEPROM to Flash. But it's very cool. I paid £20 for this. I think it's slightly more now, but you basically get this printed circuit board and all of the components, and it's up to you to solder it together. And it's just like really, satisfying to get this and solder it together, plug it in, boot it, and you get a FIG4th prompt right off the bat. It's pretty cool. So I heard that it had a 160 by 160 graphics mode, and I wanted to make a turtle graphics implementation for it. So here's the block editor. Here's some of the turtle graphics demos. And so you can see, obviously, it had the character cell video mode, but this is the 160 by 160 bitmapped graphics mode. And so, doing all of the kind of normal things that you might have done with Logo on an old microcomputer in the 80s. Pretty fun. So here's the code for it. And, it's very simple. There's really not that much interesting. There's one piece that's kind of interesting, and that's what I'll talk a little bit about. But, turtle graphics, of course, it used to be that there's a little turtle marching around on the screen leaving trails. Here we don't actually draw the turtle, but it has an X and Y coordinate and a current heading angle. And for performance, I go ahead and keep the delta X, delta Y for whatever given heading you have. So we can just do simple arithmetic to update its position. You can set the heading directly, just an angle, and we'll store that away, and we'll compute the delta X, delta Y with a sign word. So one interesting thing is the FIGnition doesn't have floating point math, for one, and it doesn't have any trig words like this. So this is a word that we wrote ourselves, and this is one of the most interesting, I guess, little bits of this thing. Worth talking about at least. And there is only sine, so to get cosine, we just offset the angle and call sine again. You can also turn by a relative amount. So you just say turn, give it an angle, and it'll add that to the existing angle and set the heading. That's usually what you do, actually. And you can have the turtle move forward. So here, you give it a distance to move forward, and it just marches along inside of a do loop, updating the X and Y and drawing a pixel at that position. And we'll get into some of the, poor performance of this particular implementation in a moment. But that's the basic idea. In a normal turtle graphics, there's a pin up, pin down, to decide whether it's going to draw or not. Instead here, we just have forward, which always draws, and then jump, which does the same thing, moves the turtle, but it doesn't draw. So it just updates the X and Y. Then just a few extra words is all to, start the whole thing, get into the right video mode, reset the position and heading of the turtle, and then end just waits for a key and switches video modes back so you can type again. And clear just fills the bitmap buffer with zeros. That's it. That was the whole implementation. And now to use it, here's some examples. First, this sine word, though, is the interesting thing. So here we're just plotting across the whole screen. It's a 160 pixel wide screen. And just calling sine for each of these increments. And you can see that it ends up plotting a pretty sparse sine wave. The idea is that this sine word, it actually doesn't take angles, or it doesn't take degrees. It doesn't take radians. It takes angles in 1/60th of a circle at a time. So I'll pick something smaller just to reduce the size of the table. And 60 is still evenly divisible by a lot of things, which makes it still convenient for turtle graphics. Iterating through just those 60 possible angles, for each of those, we're just going to jump to the middle of the screen, set the heading, and go forward to draw lines at each of the possible 60 angles. These are all of the possible angles that you can achieve with the little turtle. So you can think of it kind of like marks on a clock, like minute or second marks on a clock. So it's really easy to remember, that 15 is like a 90-degree angle, 30 is like doing a complete 180. That's the idea. So the code behind this sine function, this is my original implementation, is just a table of 15 fixed point values, so 1 byte per entry. And it's just the, the sine as an 8-bit fixed point value. Some of the poor choices made in this implementation are there's a bunch of mods happening, 3 different mods, which is a pretty expensive operation. And so Julian, I posted this to a forum, and Julian was nice enough to look at this code, and he, offered some suggestions. And so this is some of the things that I learned while working on it. One of his first suggestions is instead of a sine, how if we use cosine, which has the kind of nice property that cosine of x is the same as cosine of negative x. So right off the bat, we can just take the absolute value, and we still have to have one mod to, allow it to wrap. But that's it. That's the only mod in this implementation. So this is a cosine table in reverse order, actually, which also makes some of the other logic simpler. Now we just basically say that, obviously this table is not a complete sine wave. It's just the first, actually it's in reverse, the first half of the first crest. And now you can get the second half of the crest by mirroring, and you can get the trough by negating. So this is what we say, is if you're in the second half, then we're going to subtract that from 60. And if you're in kind of the second quarter, I guess that is, then we're going to negate. So we leave this -1 on the stack and subtract from 30 to shift everything over by half. And otherwise, we just leave a 1 on the stack, meaning it's going to be positive. So then in the end, you just look up from the table, add 1, everything's off by 1, and then multiply to set the sign. This is actually one spot that possibly could be made more efficient, but this implementation was several times more efficient than mine, which was pretty cool. The other kind of silly point that Julian made, I mean not silly, his point isn't silly, my code was silly, is my original implementation, I'm doing all of these fetches of the x and y coordinates and updating them, fetching and storing, and then calling draw, which does a fetch again, and then calls chord, which does the fixed point math by literally dividing by 256. And this is all inside of the loop as it marches forward pixel by pixel. So his idea was, how about if we just unroll all of that? It looks a lot more complicated, but essentially we can just do all of the fetches up front once, and then inside the loop you don't do any fetches or stores. You use shift 8s instead of division for the fixed point stuff. And then after it's marched forward, then you update the x and y. So if you tell it to march forward 100 pixels, it's going to do one set of fetches, sit in this loop 100 times, no fetches, and then update the x and y only once it gets to its final destination. So this was maybe 15 times faster than my original implementation. So it was a good learning experience. It's pretty interesting how just changing the algorithm can have a huge impact on performance. And so ultimately, I had some silly goal to try to get this all packed into one source block. So reducing the names of the words to single characters, so like T for turn, F for forward, that kind of thing. This all fits in one source block, just a 25 by 20 character source block, which is pretty nice. You want to load up this library, just load a single block, and then you can start to use it. So you saw the demo, but here's like some of the code behind some of those patterns that we were using. So you can see how simple it is to use. So here, I guess we're starting out at negative 50 by 50, and for 20 times, drawing a 100 pixel line and offsetting by 20 ticks each time. It ends up with this pattern. It's kind of cool, very simple. And I think this is, completely doable by, maybe young teenagers or junior high, kids. It'd be kind of a cool thing to hand this to kids. I handed it to my son at the time, and he was younger then. And it was great. He had fun playing with it, actually. Here's a little bit more interesting one. We start out with a 0 on the stack, and for 50 iterations, we just add 2 to that each time and go forward by that amount. So it's a growing amount each iteration, and turn 14 ticks each time. So each time around, it's moving further and further out, and it does this interesting little pattern. Looks kind of like a rose or something. Drawing a star is very easy. 5 lines, just 80 pixels long, 24 ticks between. And you can just draw 3 of those with 20 ticks between those. Get several stars on the screen. Even though all it can really do is straight lines, obviously you can achieve a circle just with lots of little turns. So 60 times, going forward just 4 pixels and turning just 1 tick at a time draws a pretty nice little circle. We can draw 15 of those with 4 ticks between each, and you get this nifty spirograph looking pattern. So I guess this is the most complicated one. It'd be a little bit of a pain to type that in on the 8-key keypad, but a single petal is 15 steps of little 5 pixel lines, 1 turn each. So it goes forward, turning to the right 1 tick each time, and then it continues forward another 15 steps, turning to the left. And then so to complete a petal, you basically do that and then turn 30, which is a 180 essentially, and do it again. So it goes like this and comes back. That's 1 petal. Do that 15 times with what, 4 between each, and you end up with this little flower. It's pretty cool. So Julian actually took a lot of interest in this, and he took some of the same Turtle Graphics routines to draw these patterns, and he wrote it in proper logo on the ZX Spectrum and did some performance testing. And so you can see, the FIGnition beats it handily in every single case. Most of these that have a lot of straight stretches, straight lines with not as many turns, it beats it by, an order of magnitude easily, 8x, 13, 12x. And for the ones that have a lot of turning, like these, these circles are 60 times of turning 1 degree each time. Or this one has a lot of turning also. These take minutes on the ZX Spectrum and take just a few seconds on the FIGnition. So it's like 35, 36 times faster. Much, 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 much faster. It's not really a fair comparison, I guess, because logo is interpreted and it's on the ZX with proper floating point math. But this shows kind of the power and simplicity of just this ridiculously tiny implementation in Forth on this tiny little machine, and it's way faster than the ZX, which is pretty cool. So here's the project. This is Julian's site, has information on the FIGnition, the firmware, and a bunch of examples are checked into GitHub. This is his GitHub. And there's something called the Infuse bundle that offers a bunch of software that comes pre-flashed on it, and actually it turns out that this little Turtle Graphics implementation is in Flash if you buy it through RS Components. And then just this code and this presentation and stuff are on my GitHub here. So it was a pretty fun project. It was really cool to have a completely standalone little dev environment on a board. It's totally satisfying to just solder this together and plug it in and have this thing working, and to just write fun little things for it. And it was pretty cool to hand this to my son and see him programming in Forth as a teenager, young teenager at the time. So I think it's pretty viable as a kind of an educational tool also. So anyway, it was fun.